Welcome to my 11th video in my energy series. This is on a comprehensive energy problem. We're going to do a more problem that's got a little more parts to it. It would be more like what you would see in the real world, like an engineering type problem. And the problem is a roller coaster car of mass 500 kilograms, that includes the people in it too, starts from the rest atop a 40-meter hill. So there's our hill, and there's our cart with the people in it, and it weighs a total of 500 kilograms. So we're going to ignore air resistance and friction, and we will determine the kinetic energy at the top, the kinetic energy at the bottom when it gets to the ground. The potential energy at the top, it'd be part B. Part C is the kinetic energy at the bottom. And then we want to know the speed of the car at the bottom. Once it goes down here, how fast is it going before it starts back up the hill again? Okay, so our solution here, since we have no air resistance or friction, we don't have no non-conservative forces at work. So that makes things a little simpler for us. The only force we've got is just gravity. And we have no external forces acting on the car or the tracks. So it's just gravity pulling it down. So what we've got here is in this case, as we've seen in other examples, the mechanical energy is conserved. And the way to write that would be the kinetic energy at the top plus the potential energy at the top is going to be equal to the kinetic energy at the bottom plus the potential energy at the bottom. Since these two are energy is in balance, we don't have any non-conservative forces at play that would drag things down. So now we know the kinetic energy at the top, since it's at rest, that goes to zero, because we said it's going to start from rest. Up here it's resting, no motion. And then the potential energy at the top, we remember that that's mgh, mass, acceleration due to the Earth, and then the height in meters. Now at the bottom, we really only have kinetic energy because we're down at the Earth level. So that's going to be 1/2 mv squared, and then the potential energy at the bottom goes to zero. So there's our basic equation. And what we want to do is we want to solve for the velocity. Now we can immediately see that the mass can go away. I'm going to leave it in here just for the sake of the units, but I could easily delete that and get the same numerical value. It really doesn't depend on the mass of this car. That's what it's saying. It's independent of mass. It just depends on the height. So let's plug the numbers in and see what we get out. So we get 500 kilograms, 9.81 meters per second squared, and the height is 40 meters. That's the left side here, is equal to 1/2 the mass, 500 kilograms, times the velocity squared. Now let's do the math on this side. Turn the calculator on, clear it. 500 times 9.81 times 40, enter. Okay, that is 962,200 joules, because that's going to be in energy. On the other side, we've got 250 times velocity squared. So what we can do is take this over here and then take the square root of everything. So the 9620 divided by 250 square root, that's going to be equal to our velocity at the bottom. So let's plug our numbers in and see what we get. Clear it. And we take 196,200 divided by 250. Enter. Now we want to try to take the square root of that, the second square root, and that's 784.8. Enter. Okay, so we're going to get 28 meters per second. So that's going to be our velocity down here at the bottom. Once to convert this potential energy at the top to kinetic energy down at the bottom. Remember, we're ignoring the effects of friction and air resistance. So let's see if we answer these questions. Kinetic energy at the top was 0. We just said that. Potential energy at the top was that 194,200 joules. The kinetic energy at the bottom, that was just going to be the 1/2. We can calculate that. Kinetic energy at the bottom, 1/2 m v squared. That's 1/2 500 times 28 squared. I'll just do that. So I've got 28 times 28, enter, times 500 divided by 2, that's 250. So we have got 196,000. So there's the kinetic energy at the bottom. And there's going to be some rounding errors. That actually adds some decimals, and that's why these numbers, I should have carried that out a couple more decimal places. So that's why this number should equal this number, because it is a conservative situation. I just didn't put enough decimal places in there to make that work out. So that's why the 200 is not there. But that really should be 200 there to match this. So there is the kinetic energy at the bottom. It should match that. All right, so that's the first part of this problem. Now let's do the second part. Now we're going to make it a little more involved here. Now we're going to introduce a frictional force, which removes 20,000 joules of energy. Find the speed at the bottom. So now we're going to change the speed at the bottom. So the frictional force that 20,000, that's a frictional energy. It's a force, but the energy removed from the system is 20,000 joules. So there's a frictional force that removes this amount of energy from the system as it goes down the hill. So this is non-conservative. Non-conservative energy. However, the total energy is conserved. It's always conserved. In this case, the mechanical energy is not. So the kinetic energy at the top plus the potential energy at the top, and then plus this work, non-conservative work that we just introduced here, of this 20,000 joules has got to be equal to, at the bottom, the kinetic energy at the bottom plus the potential energy at the bottom. Now, this non-conservative force is a minus 20,000 joules because it's going to be subtracting. It takes away energy, it removes energy. So our kinetic energy at the top, we know, is 0, plus potential energy at the top is 962,000. We saw that from part B earlier, minus the 20,000. Now that's going to be equal to the kinetic energy at the bottom, which is 1/2 mv squared, plus the potential energy at the bottom, which goes to 0. So now there's our equation. Subtracting these two numbers here and adding 0, we're going to get 176,000. That's the number of joules. 1/2 mv squared. Now let's rearrange this equation. We'll take the 2 over the top and divide by m. So we got 2 times 176,200 divided by 500 square root. That's going to be our velocity. Let's do that math. Two times 176,200 divided by 500 equals 704.8. Now let's take the square root. Second square root of 704.8. Enter. So our new velocity now is 26.5 meters per second. And notice that's less than the 28 meters per second from the first part, because what has happened is part of the energy going down the hill, this potential energy at the top, we subtracted this energy that goes into frictional. The frictional force essentially draws the energy away. It's a negative 20,000 joules. So the potential energy, the bottom is still zero, but now the kinetic energy at the bottom is reduced by this amount. And therefore our speed at the bottom has now been reduced by 1.5 meters per second due to the frictional force slowing it down. Well, I hope you kind of combine some of these ideas here. That was the idea of this problem, was to combine some of the stuff we've already looked at and see how they all kind of fit together in a problem. So thank you for watching, and let me know if you have any questions. Bye.